In this video, we're going to discuss electromagnetic radiation. Electromagnetic radiation is a form of energy, and there are lots of different types of energies: kinetic, potential, chemical, heat energy. So in this video, we're going to focus just on electromagnetic radiation or electromagnetic energy. Electromagnetic radiation is basically composed of two components. You have an oscillating electrical component, which you can see here, and then perpendicular to that you have an oscillating magnetic component. So each electromagnetic wave is composed of an electrical and a magnetic component which are perpendicular to each other. The wave moves in a vacuum at the speed of light. An electromagnetic wave can be characterized based on three different components. The wavelength of the electromagnetic wave is the distance between two wave peaks or two wave troughs, where a peak is a positive amplitude or the highest point in the wave, and a wave trough is the lowest point in the wave or a negative amplitude. The frequency of a wave is the number of wave peaks that pass a given point per time. So if we had a certain finish line here, let's say, and this wave was propagating or moving forward, we would count how many wave peaks pass that point per second, and that would be the frequency of the wave. And the amplitude of the wave is the height of the wave from the center, so how high the wave goes from our center point. So basically, the type of electromagnetic radiation is dependent on the wavelength and the frequency. So you can see here, this wave has a wavelength of 400 nanometers, whereas this wave on the right side has a wavelength of 800 nanometers. And you can see the frequencies are different as well. So the wavelength or the frequency determine the type of energy or electromagnetic radiation. This would be considered violet light because it has a very specific, or its wavelength and frequency fall within a specific range, whereas the wave on the right-hand side would be considered infrared light because its wavelength and frequency fall within a certain range. Now, there are a large variety of different types of electromagnetic waves, and as we mentioned just then, the type of electromagnetic wave is determined by its frequency and or its wavelength. So you can see here gamma rays, which are a type of electromagnetic radiation, have a very high frequency and a very short wavelength, whereas something like radio waves have a very small frequency and a relatively long wavelength. So again, whether the electromagnetic wave falls in the gamma ray category, X-rays, UV rays, the visible spectrum, infrared, microwave, radio waves, etc., depends on the frequency of that wave and or the wavelength of that wave. So as we mentioned here, visible light is, of course, a class of electromagnetic radiation. Visible light, of course, is electromagnetic radiation that we're able to detect with our eyes. And if an electromagnetic wave has a wavelength between around 400 nanometers and 700 nanometers, then our eyes are able to detect that. Of course, since a wavelength is a distance, we can measure that either in nanometers or meters, either one. And if you pay careful attention up here, you'll see that the frequency of the wave and the wavelength are inversely related. So as the frequency gets larger, the wavelength gets smaller, And as the frequency gets smaller, the wavelength gets longer. So these two, frequency, which we abbreviate as kind of a Greek letter, looks like a V, and the wavelength, which is the Greek letter lambda, are inversely related. As the frequency goes up, the wavelength goes down. And we can relate these two, the wavelength and frequency, to each other using the speed of light. Since the electromagnetic radiation travels at the speed of light, since it is light, we can relate them using this formula. The wavelength, lambda, times the frequency is equal to the speed of light. And the units for the wavelength are in meters. The frequency is seconds to the -1, or 1 over seconds. This is also sometimes called a hertz. So a second to the -1 is also, you'll see that sometimes called a hertz. And the speed of light is a speed, so it's going to be in meters per second. And the speed of light is a constant value, which is around 3.00 times 10 to the 8th meters per second. So using this formula that we just discussed, if we know one of these, say the frequency and the speed of light is a constant, then we can solve for the wavelength. We can rearrange this equation to solve for the wavelength. Or if we know the wavelength and of course the speed of light, then we can solve for the frequency. And you'll see, of course, mathematically these are inversely related. So one more property of electromagnetic radiation that we want to discuss is the amplitude. As you know, the wavelength of the light determines the type of electromagnetic radiation that it is. For example, here we have on the left side of the screen 3 different electromagnetic waves with different wavelengths. The top one might be red light, the middle one yellow light, and the bottom blue light. So if we change up the wavelength of the electromagnetic radiation, we change the type of wave that we have. The amplitude, on the other hand, is you can change the amplitude of a wave without changing the type of electromagnetic radiation. On the right-hand side of the screen, you see 2 electromagnetic waves. Both of them have the same wavelength, but they have different amplitudes. The amplitude, of course, being the height of the peak or the depth of the trough from our center point. So the top wave has a very small amplitude relative to the bottom wave, which has a much larger amplitude. And the amplitude, also called the intensity, determines the brightness of the light. So the greater the amplitude, the brighter that type of light, and also the more energy that wave would have. The higher the amplitude, the more energy a wave has. So the amplitude is proportional to the amount of energy for that particular wave. So let's take a look at a problem related to electromagnetic radiation. You ask, what is the wavelength in nanometers of an electromagnetic wave with a frequency of 3.45 times 10 to the 10th seconds to the -1? And what type of electromagnetic radiation is this? So pause the video and see if you can solve this problem. Okay, so in this problem we're asked for the wavelength and we're given the frequency. So we could solve using this equation. The wavelength is equal to the speed of light divided by the frequency. Now I like to solve these problems in a dimensional analysis setup. So here I have the speed of light, 3.00 times 10 to the 8th meters per second, divided by or times 1 over the frequency. So again, frequency is seconds to the -1. So I have units of seconds here and the frequency on the bottom. So I'm dividing essentially by the frequency, 3.45 times 10 to the 10th. When I do this, my units of seconds cancel, end up with meters. So this would give us the wavelength in meters, but we're asked for nanometers. So I need to convert my meters to nanometer. 1 meter is equal to 1 times 10 to the 9th nanometers. So my units of meters will cancel. And when I perform my mathematical operations, I get 8.70 times 10 to the 6th nanometers. If I look on my chart of the types of electromagnetic radiation, an electromagnetic wave with a frequency of around 10 to the 10th would fall in the microwave category. So this would be considered a microwave. So be sure you read over these sections in your text and work a few more problems so that you're comfortable with electromagnetic radiation.